Today's lesson we're going to wrap up out of the 4 different ways in which we can solve quadratic equations. We learned how to factor, learned how to graph, and completing the square. Today the last one is using the quadratic formula. This always will work. It can get messy and there are room for errors, but it does always work every single time. But the great thing is we can still keep graphing to check our work to make sure that we algebraically did things appropriately. So the quadratic formula is listed below. We first have to make sure our equation is set equal to 0 and that our beginning letter A is not equal to 0. So it has to have an x squared. There has to be an x squared to use this formula. So it's x equals opposite of b, so whatever our opposite of the b value, plus or minus the square root of our b squared, so our middle number squared, minus 4 times our first value times our third value, all over 2 times our first value. And we'll go through what this means here in the next few examples. So I have the equation 3x squared plus 2x equals 7. Find the exact solutions and approximate to 3 decimal places. So again, first I want to make sure my graph or my equation is set equal to 0 before I do anything. So in order to do that, I have to subtract 7 from both sides, giving me 3x squared plus 2x minus 7. So my a value, the number in front of x squared, is 3. The number in front of x is 2, and then c all by itself is negative 7. So notice that since 7 is negative, I bring that down as my c value. And then all I need to do is plug them in to the equation, the quadratic formula. So x is equal to the opposite of b. The opposite of 2 is negative 2, plus or minus the square root of our b value squared, so 2 squared, minus 4 times my a value of 3 times my c value of negative 7. And I just like to put parentheses around there so I don't multiply something I shouldn't. And then it's the order of operations. So I have x is equal to negative 2 plus or minus the square root of 4. Negative 4 times 3 times negative 7 is positive 84, over 2 times 3 is 6. 84 plus 4 we know is 88. I can simplify and break down 88 into 4 times 22. Because I can take the square root of 4, which is 2, and then I notice that negative 2, 2, and 6, all these outside numbers, not including the one on the inside of the radical, they're all divisible by 2. So when I divide them all by 2, I end up with 2 on the outside times negative 1 plus or minus the square root of 22 over 2 times 3. We know if there's something common in our numerator and denominator, they cancel. This gives us negative 1 plus or minus the square root of 22 over 3. And we know that when we have the plus or minus, we really have 2 answers, one with the negative and one with the positive. Using our calculator to add or subtract, then divide, I see we get approximately negative 1.897 and 1.23. And if we graph, we can see those points that are listed on our graph as well. We have x squared plus 5x plus 8. It's already set equal to 0, so I can go ahead and pull my a, b, and c value. The number in front of x squared, even though we don't see it, is 1. Then we have our b value, which is positive 5, and our c value, which is positive 8. Plugging them in, I have x is equal to the opposite of b, which is opposite of 5 is negative 5, plus or minus the square root of our b squared, so 5 squared, minus 4 times a, which is 1, times c, which is 8, all over 2 times a, which is 1. We'll go ahead and multiply. This gives me 5 squared, which is 25, minus 4 times 1 times 8 is 32, and 25 minus 32 is negative 7, all over 2 times 1, which is 2. Okay. I have a negative underneath my radical. So a couple of lessons ago back in 3.1, we say that we have to take that negative out. So that gives us square root of 7 times the square root of negative 1. We know the square root of a negative is the I. Okay. So we could say then that this is negative 5 plus or minus the square root of 7i. Okay. Or we could write it as negative 5 plus or minus I square root 7 all over 2 if we wanted to write it as one fraction. Notice when I solve here that my graph doesn't cross the x-axis anywhere. Right? That's because it has solutions that we just can't see. Let's quickly talk about the discriminant. The discriminant is the b squared minus 4ac. So when I'm looking at the quadratic formula, it's the part that's inside the radical. It tells us one of three things. If it's equal to 0 underneath the radical, we'll end up with one real number solution. If it's greater than 0, so it's positive, we'll end up with two different real number solutions. Or if it's negative, such as this last one we had was negative underneath the radical, we end up with two different imaginary number solutions, right? One with a positive and one with a negative. There may be times when we come across equations that look like quadratic equations, but they're not listed as such, so we can make them into quadratics. And we're going to let u equal x squared. So we're going to let u equal x squared. Then if we were to square our u and square our x squared, we would see that u squared would then equal x to the fourth. So I'm going to replace my x values with my new modified u values. So I'm going to replace x to the fourth with u squared minus 5 times, I'm going to replace my x squared here with u, so minus 5u plus 4 equal to 0. So now I've made it into quadratic form, and that we can do something with it using one of our techniques. So I'm going to factor this one, because they look like numbers that are easily factorable. Find two numbers that multiply to 4 and add to negative 5. Looks like negative 4 times negative 1. There's nothing in front of u, so I can move to u minus 1 and u minus 4 equal to 0. We know that once it's factored and it's set equal to 0, we can set each factored form equal to 0. So u minus 1 is 0 or u minus 4 is 0. Solve for u. So we'll add 1 and we'll add 4. But uh-oh, we ended up with u is 1 and u is 4, but our original equation had x values. So let's turn it back into x. So I'm going to replace my u back into x squared. So x squared is equal to 1 and x squared is equal to 4. And then we're going to go ahead and get x by itself by taking the square root. And the square root and the square cancel one another. So when I take the square root of 1, remember when I take the square root, we need a positive version and a negative version. So I have positive 1, negative 1, or positive 2, negative 2. When I graph this, I see that I have my negative 2 and my positive 2, my negative 1 and my positive 1. So this was a W-shaped one because it's a quartic function because there is 4 solutions. So it does not surprise me that I should end up with 4 solutions down here. Let's try another one of those. Here I have t to the 2/3 minus 2t to the 1/3 minus 3 is 0. So what I'm first going to do is let u equal t to the 1/3. Notice how I'm using my middle term here. Therefore, if I were to take u and square it, and take t to the 1/3 and square it, I would end up with u squared equal to t to the 2/3. Since 1/3, remember power to power we multiply, so 1/3 times 2/1 is 2/3. Replacing my t's with u's so that we can actually do something with them. I'm replacing my t to the 2/3 with u squared since they're equivalent, minus 2 times u, because t to the 1/3 is equivalent to u minus 3. So I can factor now, find two numbers that multiply to -3 and add to -2. Looks like -3 times 1. So I'll have u plus 1 times u minus 3, setting each factored piece equal to 0. I have u plus 1 is 0 or u minus 3 is 0. Solving for u, I'll subtract 1 and add 3. So u is equal to -1 and u is equal to 3. But we're solving for t, not for u. So I need to plug back into t. So t to the 1/3 is -1 and t to the 1/3 is 3. We're going to eliminate that power of 1/3. We're going to multiply by 3 because we know power to power we multiply. So 1/3 times 3/1 is 3/3, which just gives me the power of 1. So when I multiply these two powers together, I'll just get the letter t. And -1 times -1 times -1 is 3. Again, when I multiply, I get regular t, and 3 times 3 times 3 is 27. So my solutions are -1 and 27. When I graph it, it gets me a really weird and awkward looking graph, but I do see that I cross at -1 and at 27. Okay. A word problem. The number of museums in China increased from approximately 2,000 in the year 2000 to over 3,500 by the end of 2012. In 2012, a record of 451 new museums opened. For comparison, in the United States, only 20 to 40 new museums were opened per year from 2000 to 2008. The function given, so this is going to be a good explanation for what a model might look like. So to model this data, this function can be used to estimate the number of museums in China X years after 2005. So this h of x part represents the number of museums, which is our y value, and our x value represents the number of years after 2005. So x represents our number of years. Okay. So estimate the number of museums that will be in China in 2017 if the number of new museums that open per year continues at the same rate. So if this model continues to be accurate, what will the number of museums be? So we're looking for y here, and from 2000 to 2005 to 2017, the number of years that have passed has been 12. So I'm going to plug into 12 my x value. We can multiply and divide, multiply, square using our order of operations. So when I plugged in 12, I ended up with approximately 6,807 museums in China. So in what year, so here we're looking for our x value, and what year was the number of museums in China 2,600? So we're given the number of museums, so we're given our y value this time. Our y value is 2,600. We need to know in what x value of year will give us 2,600. So I need to subtract, because I know with whatever method we need to set it equal to 0. So I'm going to subtract 2,600. When I subtract 2,600, I get the function 0 is equal to 30.992x squared plus 4.108x minus 305.406. So let's use the quadratic formula here. My a value is the number in front of x squared, my b value, and my c value, which is negative. Plugging them in gives me the opposite of b, so negative 4.108 plus our b squared minus 4 times our a value times our c value all over 2 times our a value. Using the order of operations and multiplying, I end up with negative 3.206 or 3.074. Since x represents the number of years, it does not make sense to use the negative value, right? So since it doesn't need the negative value, the only option it could be would be about 3 years. They would reach 2,600 museums. So 3 years after 2005 would be 2008. I can see that when I graphed my equation from here, based on the data that I want, when I graph it, I did end up with these two x values. Note that we're not using the negative value because it does not make sense in the context of the problem in which we are given. The number of both magazine launches and magazine closures have increased in recent years. The function m of x is equal to 34x squared minus 59x plus 81 can be used to model and estimate the number of magazine closures after 2012. In what year was the number of magazine closures 99? So this m of x represents the magazine closures. So that's our y value, and our x value represents years after 2012. So it's good to identify what does our x value mean, what does our y value mean. So here we're given the number of magazine closures, so as 99. So I'm going to replace my y value with 99 because I know my y value represents the number of closures. And then we can solve for x by using the quadratic formula. So I'm going to subtract 99 from both sides, giving me 34x squared minus 59x minus 18. Our a value is 34, our b value is negative 59, and my c value is negative 18. Plugging them in, the opposite of negative 59, so the opposite of negative 59, notice that this turns into a positive, plus or minus our b squared minus 4 times our a value of 34 times our c value of negative 18 all over 2 times our a value of 34. Multiplying, I see 2 times 34 is 68. 5,929 when I simplify inside my radical is a perfect square of 77. So I have two options. I have 59 plus 77 over 68 when simplified is 2, or 59 minus 77 over 68, which is about negative 0.3. Well, since our x value represents the number of years after 2012, it doesn't make sense for our years to be negative, so we can ignore the negative value. So the number of years after 2012 is 2, which would give us the year 2014, when there would be about 99 closures during that year. I can see when I graph that I end up with both the negative value, which doesn't make sense in the context of the problem, and the positive value to help us. And now you can successfully complete the second part using the quadratic formula in our lesson.